All right, hi. So this is the video on instruction opcodes and how you do what we call disassembly. Um, Now, before we start talking about disassembly, let me go to the manual and show you the different memory architectures, sorry, memory structures that are there. So in the manual, basically we had this schematic which is like this, right? And here we had a program memory which is pretty big, and the address bus is 24 bits, and you have your data memory which has an address bit that is roughly 12 bits, and you basically read instructions from here, instructions that say move, add, and so on, and do operations here on the data memory. And the data memory includes the uh, W0 through W15 registers, and it also includes all kinds of registers that you put your variables in and so on. So pages 33 and 34 talk about the data memory. So this is the smaller memory that we had. And you can see that from addresses, maybe it might not be visible well. Let me just increase it to maybe 100%. Okay, so if you look at the data memory, visually we show it as words, which is 2 bytes, right? And usually we show least significant byte here and the most significant byte here. So when I say address 00, I usually use address 00 and write it here. I really mean that this is address 0, this is address 1, and then the next line I write 0002, and I mean this is 002, the least significant bit, and 003 is the most significant bit. So addresses from 0 to 15 are going to be your W0 through W15, and then after that you have a bunch of data elements, some registers that control how the timer works, how the CPU clock is configured, and so on. And then you get to the first empty location, unassigned location in data RAM, which is 800. This is where you put your variable. So var 32-bit goes here, and so on. So this is the space that you would use for your own data uses. And then the data memory goes up to 1FFFF. So this is the last um, data memory location that you have in the physical memory. And you can know that this is 13 bits. But if you're dealing with words, then you know that your words are going to be aligned to even addresses. So a lot of times, even though my address is 1FFFE and requires 13 bits to represent, I can represent it in 12 bits and just skip the least significant bit, and you would know what I'm talking about, right? So we'll come back to this point later, but just keep in mind that the data space, the physical memory that you have, ends at 1FFFFH. And then you have these unimplemented. So if in your program you say give me the value of data memory location 2900 hex, it's going to return all zeros. Now there is a trick that the microcontroller plays, and that is if you use these high addresses like 8000 hex, there is no such physical memory at the data memory that corresponds to this address, right? There's nothing in hardware that gives you data there, but the microcontroller then knows that yes, indeed, I'm trying to access a shadow of the program memory. So if you have constants in your program memory, like the text messages that say please wait a minute, right? I mean, please wait a moment has to be stored in the program memory in the form of character ASCII bits. Or if you have some constant values for calculating sine and cosine and numbers like that, then you would put that in program memory, which goes into the flash memory. And then there's a trick that you can play to map part of that program memory into this data memory, And of course, there are tricks that you have to play because the addresses don't match. If you remember, the address for the program memory was 23 bits. Here you're dealing with only 12 bits of data memory address and so on. So we will get to this trick later. In discussion 3, we'll go over one example that does this and shows you how to use the program memory mapped to data memory. And this is the predefined registers that you have, right? So this says these are the core registers that talk about how the CPU is configured. These are timers. So look, address 100 hex, right? Then you have UART, you have analog to digital conversion, and so on. And each of these segments of the memory, they have a bunch of registers that you control things in, and you would be able to say, here's the behavior of timer 1, here's the behavior of timer 2, and so on. And the following tables are showing you the details of these registers. So these are the core registers, then you have the interrupt registers, then below it you're going to have timer registers. And over the course of the semester, we are going to go over many of these, and you're going to see examples that talk about, how you configure the different peripherals that we have, different units that we have. Now, so if you go to page 31 of the data sheet, this talks about the program memory organization and how the PIC microcontroller expects you to tell it, what to do. We haven't covered interrupts yet, but interrupts would say these are the addresses that I want you to go in the event of an emergency of type 1 or type 2 and so on. And then you have flash configuration words. These are things that are used even before your program runs. So like, this is the clock frequency that I have. Do I want to go into sleep mode to do power saving or not? These are the things that are going to go there. But mostly you will be dealing with this user flash memory, program memory. I leave it at that. When we get to implement programs using interrupts, we'll come back to this picture and I'll talk a little bit more about these. And basically you'll see how to use the different memory locations. Now, the program memory, the opcodes that you put, the things that you put in move a literal into W0 or add this to that, are basically implemented in program memory using 24 bits of the program address. And this is not implemented in physical memory, but they tag along zeros so that you can talk about a 32-bit program value that you have. All right, now, so this is the memory organization, and basically what we're going to look at is when you write move a literal into W10, what goes in here, right? And let me just one last time show you the architecture and just remind you that those 24 bits of the opcode, like move W1 to W2, that goes through an instruction decode that tries to understand what you mean by the values that go into this program memory. So we are going to look at this process and the stuff that you write here that gets interpreted here, and you can see things. Now, before we do before we go over a program, let me show you how to see the program memory contents. So basically here in MPLAB-X you have window, and then you have the PIC memory views, and then choose program memory. Right? If you do that, then you're shown a window here, and here you have, of course, memory you chose to do program, and then in terms of the code, you could either say hex. So hex is the values that you're actually writing into the flash, and it could work with these, but not very user friendly, so it's easier to choose the code. And if you choose the code and enlarge these, then you can basically see the instructions that you have here and the opcode. This is the value that goes in the program memory at this particular address. Okay, and let's go ahead and start looking at some of these instructions and see how they get translated. So in discussion 1S, let's just skip the first instruction. This is a tough one. Let's move on to move, stack, and W15. Now, if you remember, the pound sign means I have a literal, right? I have a value that I need to move to W15. You don't need to go to the data memory to get this value. That value is already included in the program memory. So when you say move stack, you can see that the compiler really did move 808, and that should not be surprising when we defined stack, right? So these started at address 800, and this takes 4. This starts at 804, but you align it 2. So this one is going to start at 806 and has a space of 2, so a stack is going to start at 808. So that's the literal 808 that you want to put into your W15, right? So now the question is, how do you translate that to this 20808F that goes into the program memory? And once you do that, once you put 20808F in the program memory, once the microcontroller reads that value, it has logic in the decode, in the instruction decode that understands, oh, yes, I see, with 20, you really mean move. What value should I move? Well, the value of 808. What register should I move it? Register 15, right? So it's really that process. There's some logic that decodes, that looks at these opcodes. These are called opcodes, 20 for move. And basically there's hardware that does the translation for you. Now, how do you go from this move 808 to W15? Well, you can look at the programmer's reference manual, and page 40, you have a bunch of move instructions, but which one of these moves is it that we are doing here? So if you go back to the code, we have move a number, a large number. So 808 is going to be a large number. It's not going to fit in 5 bits or 10 bits. And then you have one of the registers, one of the special purpose registers. So then it's going to be this instruction, move literal 16 into W and D. And you go to page 284 here, and it says that the encoding is going to be like this: 0010. So binary 0010 would be hex 2. Let me go back to the code. You can see hex 2 appear here, right? And then it says I have K, 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 right? These are 16 bits of K. And this is the literal. So it says the 16-bit literal K is loaded. What is the literal? Well, the literal is the address of a stack, which is 808. So you can see 0808 appear here. Alright, so that's the constant that you had, and then the manual says DDDD is the register number, so it goes from 0 to F, 0 to 15, right? And our instruction here says W15, so I need to have F at the last element, right? Alright, so this one was easy and straightforward, but it's going to get a little bit more complicated, and we'll get to them one by one. But one question that I have in coding, so I mean, either you write move a stack W15, or write move number 808. Of course, you want it to be hex 0x80x 808 into W15. These two lines of code are exactly the same for this particular code, right? Because you know that a stack is going to be located at 808, so these are going to translate to the same thing. But this would be dangerous. Never do this, because 808 relies on the fact that, first of all, the compiler is going to start putting this first one at address 800, which is true in this version of the compiler, but who knows, maybe in a future update they decide that we do need address 800 for storing some of our compiler related stuff, and your variables will start at hex address 810. Right? So that's one thing. The other thing is you don't remember that you hard-coded the value of a stack in your code, right? So let's say somewhere along the line you say, well, I need var a, and I need to, dedicate a space of 10 to it, right? Then basically if you do that, you've messed things up. A stack is no longer at 808. It's going to be 808 plus 10, and your code is going to be wrong if you had used that hard-coded move pound 808 into W15. Okay, so as long as we are clear that 808 is not a safe way of doing it, this is for just educational purposes. I'm showing you this move 808. Now, what happens if I say move not the pound sign, but actual 0x808 W15, right? There's a big difference between these two. When you say move number 808, then that means that the value 808 is hard-coded into the opcode itself. 808. So you can see that the opcode here says 808. But when I say move 0x808, what I really mean is go to data memory address 808. Whatever value is stored there in the data memory, let's say the value is 3333. Move that 3333 into W15. Okay, so these are very different instructions. And if you do that, then the opcode should come out differently. So in fact, we can go ahead and do that and compile this, and you're going to see that you're not going to use the opcode 20 as we used for the number 808, but we're going to use a different opcode completely. And let me go to program memory here. Alright, and now you can see that these two lines both translated to move pound 808, which is showing that a stack and 808 are the same thing. And then you have move stack to W15, right? So it translated the one without the pound sign to, and it was smart enough to know that 808 corresponds to the address of stack. And you can see the address here is, the opcode here is 80404F. Okay, let's dig deeper and see what happens here. So if you go to the Programmer's Reference Manual, page 40, you can see that now the move pound 808 was this instruction, but now you're not using the pound, so you really mean move a general purpose register F into WND, and that F is at address 808. So if you go here, you can see that the opcode is different. You have 1000, which is 8. Let me go back to MPLAB and show you this is 8. So if you want to write down on a piece of paper, if you can't read it off the screen, it's 80404F. Okay? Now, so the 8 does make sense, right? Now the rest of it seems to be a little bit weird. So we have a 0 here, and then we have FFFF, 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 right? So this has 12 plus 13, 14, 15 bits to represent F. And of course, the data memory doesn't have that much physical memory space, but that's the program memory mapping thing that we're going to get to later. But now, as far as we are concerned, we want to put 0808 here, and then DDDD would still be F. We are putting into register 15. So you expect to see 8 as the opcode, 0808 here. But look at MPLAB. It shows you 404. Right? Why is that? Well, if you remember, I said that if you're dealing with words, which are 2 bytes, then your addressing has to be only on even addresses, right? So if that is the case, then why bother wasting that extra bit that you know that always is going to be 0? So instead of 808, you just shift it and say 404. 404 is basically 808 divided by 2. Okay? So that's why your program shows, the opcode shows 80404F and not 80808F. They're just trying to save one bit in the program memory. So it's good that we talked about this word address and even addresses and the shifted value of 808 becoming 404, because then we need it in more complicated versions of it. Let me stop here and record another one continuing on the same thread.